All right, in the past we've talked about usually linear or circular kind of motion, but now we're going to kind of delve into rotational world of something rotating. And in the past we've had some variables um, um, displacement, which was given by the letter D, and we were given by velocity, which was given by letter V, and we talked about acceleration, which was given by A. But now we're talking about some object that is rotating. It's not actually moving to a new location, it's just rotating. So instead of talking about a linear distance that it's traveling, we're talking about an angular displacement. You know, how many radians has it traveled? And so the symbol we use for when we're talking about rotational world is going to be theta. It's going to represent an angle, how many angles we've gone around, and that's going to always be in radians. Remember, these over here, d was in meters, velocity was in meters per second, and acceleration was in meters per second squared. So in rotational world, we have theta, which is going to be in radians. Technically, it's not really a unit. It's just the number of radians or radii that it travels through. But I like to write RAD because kind of having a label. So then we have velocity, and so that's going to be, you know, how fast is it rotating? How many radians is it turning per second? And the symbol that we use for that in rotational world is omega, and that's going to be in radians per second, how many angles per second. And then we can make this go faster and faster and faster and faster, spinning around, and we can angularly accelerate it, which instead of an A is an alpha, and that will be then in radians per second squared. And so this really, I hope you agree, is really, really easy. It's just doing all the same equations, but instead of talking about something traveling from one location like the next, we're talking about something angularly, moving or rotating. So we've had equations in the past. Our constant velocity when we don't have any acceleration is d over t. That's constant velocity. Hopefully remember that. And then we had three what we called uniform acceleration equations. The uniform acceleration equations. We had three of those, if you remember them. We had VF, final velocity, equals VI, initial velocity, plus AT. This is the one that did not have displacement in it. We had displacement equals VIT plus 1/2 AT squared. You'll notice this is the one that did not have a final velocity in it. And then we had VF squared equals VI squared plus 2AD. And of course, this is the equation that did not have time in it. So what we can do is we can use all these same equations, and it's funny because a lot of these equations are given in textbooks and they're written a different way, and people make it seem like they're completely different. They're not used any differently. We're just talking about something rotating rather than something moving like in linear motion. So we have a constant rotation velocity equation. Velocity is, omega equals theta divided by time. So it's how many radians we're turning, how far did we turn around, how many radians did we spin, in how much time, and that'll be radians per second for the omega. So then all these equations just have a corollary equation that's the same. So I have final angular velocity equals initial angular velocity plus alpha, angular acceleration, times time. Or I could have the amount of radians we turn, angular displacement, equals initial omega times time plus 1/2 alpha t squared, or angular acceleration, and then times squared. Or I could have my final angular velocity squared equals my initial angular velocity squared, plus 2 times angular acceleration times the angular displacement. So these equations, they're exactly the same. You use them exactly the same. I tend to think of these equations and don't even think of them in this terms usually. I just talk about an initial velocity and a final velocity, but I think about we're rotating in this case when we're going to use these particular equations. Okay, so if you can just remember these equations here, we're going to go ahead and clear this page out, and we're going to try a couple of problems. So let's say that we have something that is rotating, and let's say that it moves from rest. So that means its initial angular velocity is 0. It's not rotating, and then its final angular velocity is 725 revolutions per minute. And let's say it takes a time of 10 minutes to get from 0 to 725 revolutions per minute. And the first thing I want to do in this problem is I want to figure out what is my angular acceleration. Okay, just like all the other units had to be, all the other like velocity, distance, time, all they had to be in certain units, it's the same way with angular motion also. All angular displacements need to be in radians. So angular velocities need to be in radians per second. So this one's fine, but this one here we need to convert. So we have 725 revolutions per minute. And we know that one revolution, which is one turn, we have something that's turning one time, one turn is a little over 6 radians. To be specific, it's 2 pi amount of radians. And which is okay, so our revolutions cancel out. But we have minutes on the bottom, and we need seconds on the bottom. So we're going to put 1 minute on the top and 60 seconds on the bottom so that minutes cancel out. So I take 725 times 2 times pi divided by 60. And if you do that, you'll figure out your angular velocity is 75.9, or about 76 radians per second. Now, the radians technically isn't a unit, so I could just put 1 over s, or I could put s to the minus 1. But technically, it's radians, radii per second is my angular velocity. My time, it cannot be in minutes. It has to be in seconds, so that's going to be 600 seconds. Hopefully, you can convert that quickly. So what's going to be your angular acceleration? Well, it's final angular velocity, 75.9, minus your starting angular velocity, but that's 0. And you divide that by the time, which is 600. So our angular acceleration is going to be 0.126 radians per second squared, or I could write s to the minus 2, radians per second squared. So that's how I can figure out my angular acceleration. Let's take this problem a little bit step further, and let's say how much will it have rotated? What's the angular displacement if we let it accelerate like this for, like, let's say 15 seconds? For 15 seconds it accelerates like this. What's our angular displacement? Well, I need an equation that has angular displacement in it, and I could use angular displacement equals initial angular velocity times time, but that would be 0, plus 1/2 angular acceleration times time squared. So this is the equation I could use. I could do 1/2 times 0.126 times 15 squared, and I would get an angular displacement of about 14.2 radians. 14.2 radians, which would be, it's like a little over 6 radians to go all the way around once. So twice would be 12. It'd be a little over 2 times around the circle that it has rotated. So that's how we can use those equations. Let's do one more problem. Let's say we have a wheel and it's angularly accelerating, so alpha, of 8.4 radians per second squared. And I want to know how long, so time equals question mark. How long will it take for the wheel to attain an angular velocity of 6 revolutions per second from rest? So your angular initial velocity is 0. So how long will it take this to happen? This is a pretty easy problem. We know time is going to be angular velocity final minus angular velocity initial over our angular acceleration. The only problem is here we don't have this in the correct unit. 6 revolutions per second needs to be in radians per second. So 1 revolution is 2 pi. And I can multiply those together, and I'm going to get an angular velocity of like 37.7 radians per second. And so I can put that in for my angular velocity. My initial velocity is going to be 0, so that's gone. And so my time would be 37.7 divided by my angular acceleration, which is 8.4. And if you do that, you'll get a time of about 4.5 seconds. So we just apply these uniform rotational acceleration equations exactly like we applied our regular linear uniform acceleration equations. It's just we're talking about something rotating, and if we can keep that straight, we just do the same kinds of problems all over again.